So, good morning. See, recording is on. Good. Welcome back to QBI. Today we are going to talk about shape analysis. And what we want to do is not only to make images nice, segmented into black and white, we want to know more. So now is the question how we can quantify how big different objects are, and possibly we can tell something about what its shape is like. Maybe we want to compare objects of different sizes and see how they behave, if they are placed in different places and so on. And even go one step further, comparing different images. And so maybe we even want to do some finite element analysis on the images that we have prepared until now. So this is what the first part will be about. And what we are going to look into is object characterization, measure volume, also finding center and extents, looking into an anisotropy, and so on. So first thing, we have now processed our data. We did something where we got an acquisition of a lot of data, so say 56 gigabytes per sample. There can be many of them. Then we did some filtering, which still produced large data, but now we have doubled it because we have two versions, the original and the filtered one. Then when we go to the segmentation, then it gets more interesting because then we have reduced the data down to less than 2 gigabytes per sample. 2 gigabytes is still quite a lot, but you can at least keep it in your laptop. And now we want to reduce this radically. And the reason to do it is actually we want to measure something. So we want to have some single scalar numbers in the shape of a table or something. So it could be volume fraction of the data, cell count, maybe stretch of the cells, or variations in cell size and volume. So what we want to do is actually finding possibly some hidden objects. We want to do some measurements, counting, maybe checking how things are mixed in the data, or even in time series track changes of all these things. The metrics we can look at now are plenty. We can first of all look at the surface area. Depending on if you do it in 2D and 3D, look a little bit different. But in principle, so surface area in 2D is just the whole number of all the number of pixels. If you look at it in 3D, then it's just a shell around the object. Counting is also an interesting thing we can do. And then, as you can see, there is a long row of things we can measure quite easily, actually, using these images. Some literature. We have this Jean-Claude morphometry with R. The language so R is actually a programming language which is used a lot in statistics. While it was more or less competing with Python, but I think nowadays more and more people go towards Python, in particular in the field of image processing. But there are a lot of interesting metrics and theory in that book, so it's still worth looking at. John Ross, as always, has a lot of information, has this brick, so there is a lot. Then if you want to look at principal component analysis, then this would be a book, and yet another language, S, which is related actually to R. So S is the commercial version, R is the open source version of more or less the same language. But still, it's one thing that it's about using some specific language, but the ideas in these books apply as well to Python, and you can also easily, I would say, find the similar functions in Python. Then there are some more papers to read if you want. And I believe there is even more. Yeah, there's a bunch. Some are books, some are papers. And yeah, let's see. This one I think is based on ImageJ. So if you want to work with ImageJ, this would be a book to look at. And Jane, I don't think he did any newer books, but it's actually a pretty good book, particularly on the field of filtering. But he also has some things about the morphometric tasks. Of course, usually we need a bunch of modules. In particular here now, let's see, we have this region props and label. They are probably the most interesting today. Another one is the principal component analysis, which we have down here. It's also something new that we haven't been looking into. Otherwise, it's all new, known stuff, I believe. And well, there are some things for the visualization around here and down here, yeah. But the main interesting things are label, region props, and PCA. So, if we want to have our black and white image, the first thing we need to do in order to measure anything about its items is to label the items. Until now, we only have one block which is background and one block which is foreground. The labeling puts a name or index number on each object in the image. And it could be an image like this, where we have first the bi-level image, where you can see everybody are yellow. And then if you run this label, then you can see that they got different colors, and each color corresponds to a label. So this is what we want to do with our data. We could have a more natural image. So this is a picture from, I think it's from Heidelberg. But anyway, you can see a cityscape where we have some cars, and someone did the labeling or segmentation for us already, so we can see all the cars. We actually don't care much about the cars, it's just that we have an image right now. And this one you can see that we have some white blobs. Some of them are actually cut in the middle. This one is cut even twice. I think it's because of the trees or something back here. But at least we have identified the cars. And in Python, and in particular scikit image morphology, there is this function label, which has a very long manual help page. So first thing, when you have a function, one thing is you can go to the web page, but if you want to do it on the prompt, you can just type help and the function name, and you get a very long list of information about it. And the interesting thing is they are talking about connectivity here, and there are different kinds of connectivity that can be used, and that's in principle talking about the neighborhood which is probed in order to do the labeling. We will look at that in a few slides later. And well, there's a lot of parameters, but I'm not going to show them much more. So if we run this label function on the cityscape, on the segmented cityscape, you can see here that we got a lot of labels. We got blue for the background, and then we got green, orange, and so on. And you can see even down here, the cars that were cut by the trees or poles of the traffic signs, they actually got several labels. So you can see already that this may not be always what you want. So there may be better methods to do it. But today we are only going to talk about this component labeling method. So what we're doing is, based on this, we can compute the area of each segment, and the area is, in principle, we have our image, and for all coordinates that belong to class I, we just count them. And that can be quite easy, so we can just sum up this as a function, and afterwards we get a nice table where we see label how many pixels each label has. And another way is to use the histogram. So if you create a histogram of the image, of the labeled image, with as many bins as you have labels, then you can get the counting much quicker. Instead of writing this code, you can just do a histogram. So that's another way of getting this counting, because the histogram counts pixels of corresponding to each bin. So, and the algorithm for doing this, there are very many ways of doing it. But let's start out with an image looking like this. So we have just a black and white, and it's kind of a cross without a center point. And this one we want now to label the different branches of this cross. To do it, we can have different ways. Is this really the slide that should be here? Just have to check one thing, sorry. Seems like I got some sub-slide that was... No, that was right. Okay, sorry. So, what we have is, for each point in the image, that's the initialization. For each point in the image belonging to the foreground, we set a value which corresponds to its pixel index. So the pixel index is x plus y times the width plus 1. And then you can see here that this corner pixel got the value 1. This got 9 because it's 8 plus 1. And then it's so on. And you can see here that we got an index number for each of these pixels. So this is the initial state for the segmentation, for the labeling. And the algorithm as such, this is one algorithm to do it. Maybe not the fastest, but it's easy to show how it works. And so for each point belonging to the foreground, then we look in the neighborhood around it. So all the pixels, depending on which neighborhood function we have chosen. Could be that we have just the four connectors, so we just have a cross. We could also have a box, and you will see later what different neighbors and their effects will be. And then if the neighborhood pixel belongs to the foreground, then set the label of the current pixel to the maximum of the 2 pixels. And then you repeat until you have no label changes anymore. The implementation of that, I actually do some cheating, because looking around the neighborhood requires a lot of loops, and the code becomes quite unreadable. But the important thing is that we do some iterations that we decide. Then the first step is to do a morphological dilation. So the dilation is when you have the pixel, then it will grow up the area to the size of the footprint. And in this case, it's grayscale dilation, and the grayscale dilation is in principle a maximum filter. So the pixel value you get on the pixel you look at is the maximum of its neighborhood. And then you make some list and can do some grouping and then update the image. So this will be iterated a couple of times. And a little trick here too is I need to multiply by the mask, because otherwise it will grow all the time. So what's happening in this is we can see we have some iterations, and with this specific case, the branches are only 4 pixels long, so we can actually do this within 4 iterations. And you can see with iteration 0, we have the original initialization, and with the iteration 1, you can see that some of them starting grouping together. So these parts of the branches, they are getting now the same number, and same down here. And the reason why it's coming from below is that we have a maximum operator. So this one gets the maximum of that one. And you can also see that the maximum is shifting up because the 11 moved up here and the 21 moved up here. And then after the 4 iterations, we get now 4 different labels plus the background. So it will be 31, 33, 73, and 81. And this one quite quickly converges, and for this small image, we have it within 4 iterations. How quick it iterates depends, of course, how large the objects are. And it, of course, takes longer if it's more complicated. And there are quite many different algorithms to do this. Some can do the whole labeling in a 2 and 3D image in only one scan through the image and one scan back through the image. But that will require quite some more code to write, and I didn't want to show it here. So let's look at something bigger. Now we have this, looks like a Space Invader, but it's one of the cars from the cityscapes before. And the original one is just zeros and 1. Then we do the initialization like we did before. And after running this brush fire, we can see that we have some number of groups, and we got some changes. And after 7 iterations, this labeling was done. And looking what's happening, you can see this animation, and you can really see how it's like a brush fire that propagates over the landscape. And in the end, it will label this car into 2 pieces. Now, if we change the neighborhood, so this was using a neighborhood of 3 by 3, and so it's 8 connected neighborhood. Now, what if we do instead a 5 by 5 iteration, 5 by 5 neighborhood? So now we are taking it one step further away, so we have a second ring around the neighborhood. The first thing you can see is that the number of iteration got less, and that's because we have a larger area to work with. And looking at the effect of it is that the brush fire now actually labels both pieces. So it's actually, thanks to this larger neighborhood, it now actually bridges the gap between the pieces. Can be what we wish for, but not always. So using larger footprints may be a choice for the moment, depending on your task. The other way would be to look at a smaller kernel. So now we're just looking at the 4 connected neighborhood. And the first thing you can see when you run it is we have many more iterations. Of course, with smaller neighborhood. So if we run that one, you can see that the brush fire is moving on. And the interesting thing is, now we get actually, look at this one, you can see that this has a different index or a different label than that block. And that's the reason for that is that the cross can't fetch the bridge between this free hanging little pixel. So in this case, we get 3 labels instead of 2 that we got with 3 by 3. As a comparison, we can see here now that we needed 9 iterations for the first one, the 3 by 3, and then we got 5, and then we got 14. and the number of segments also got different. So it's really depending on what kind of neighborhood you're using, and that's in general when you start working with neighborhoods, it will have an impact on the output. Usually what we are using is either the 8 connected or the 4 connected neighborhood, or the analogs in 3 dimensions. The 5x5 is more a rare thing, but it was more to show that you can bridge the gaps in that way. So now we got the labels of different things in the image, and the question is what we can measure. And one is of course measure the volume, and also looking at changes of the volume when you do erosion and dilation, and with that you can actually get the surface area or the perimeter length. So now we want to do some measurements. We can count the cell, we can say something, but how to continue. And one thing is we may want to know the position of the object. And here we got now the labels, and 1 and 2 of this object, and that was clear. And now we just want to look at a single object. And to define the center, we need to compute some weighted average actually. So the coordinates you get for all pixels belonging to a certain ID, you compute this sum for x, y, and z. And in principle, that will be the average position in each direction. And looking what it looks like, we can see here now we are doing this for all pixels belonging to label 2. Then we sum up and compute the mean of that. Or actually, we collect the pixels, so this is a list operation. The reason for making this list is more to show, to create the table. Otherwise, you would probably just compute the averages directly in the image, from the image point. But if we have these lists, computed the average, we can see that the average position within this gray area, which is correspond to label 2, is actually makes sense pretty well. So this is a way how you can compute it. Usually you don't have to write this loop, so it's already included in the scikit image. Then another alternative is to look at the center of mass, and now instead of just counting or averaging the positions, you can now weight every position with a gray level in the item. And then of course the sums become a little bit more complicated, so we have the position weighting and the gray level weighting, and everything is divided afterwards by the average gray level in the object. So that one wasn't executed. Let's see. Yeah. Okay. I hid the code. In principle, let's see. Is there one more? No. This should have been executed. Yeah, somehow it was hidden. So in this case, we are just taking a very simple box, but there is a gradient within it. And if you segment that, you will get a black and white image, and we will compute both the weighted average, gray level weighted, and just the center of volume. And then I can switch over here again. I think I have a problem with my display today. Sorry for that. But anyway, looking at the differences, you can see that the center of volume is very much in the middle of the square, but the center of mass has displaced a little bit. This, which one you use depends on, again, on the application, but to be honest, personally, in most cases, I have only used the center of volume, center of mass. There can be applications. If you have maybe some cell density or something that changes with the intensity. So let's go back in display mode. So, of course, we can do a lot more than just what we have looked at here. We can look at the area, which I showed. Also, what we also can look at is the perimeter length, sphericity, orientation, and these and many more things we can get through the function region props, which is available in scikit-image, and in particular in the measure subsection. And it has pretty many different, let's see, yeah. So here you see all with the double star are the different metrics that you can measure. Right now I'm not going to read them up, all of them, but you can see that there's quite a good collection of different metrics you can get. And when you call it on the different items, you can see here that you can get the area, bounding box, convex, etc., etc. So this information you can easily extract and create tables when you analyze your images. And of course, this information tells things about the images, but it may be too abstract and too far away from what you actually want to see. And often it's not so interesting to know how large something is in the x direction or in the y direction, because if you have something that is elliptic and you look at the x direction, it doesn't really make sense. So you need to know at least along the principal axis of the object. So here we can get some properties, so we can specify at least what we want to look at. Looking at here, the area, perimeter, and centroid, and then we get this table. So you don't have to get the whole list. It can be too cluttered, actually. And looking at the extents is another way. So we looked at first, now we looked at the center of volume or center of mass. But sometimes it's sufficient just to know the extents, in which little area you look at of the object. And looking again at the car item, and if we want to see the area of extent of it, then yeah, there is a little bit of code here. But in principle, we are extracting the coordinates of the car, and then we look at the minimum of the x-coordinate, maximum of the x-coordinate, and same for the y-coordinate. And then we can see what are the corner points of the object, and we can draw something like this, where you have these coordinates. That can be useful, for example, if you want to do some analysis where you crop the object, and then you want to create many small mini images of all the items. The application of it could be, for example, if you have a grain packing and want to simulate new grain packings, then you can take all these tiny objects and bring them into your simulation. So that could be one application of it. And Another thing, so if you want to look for faces, you want to crop out the faces of people, that could also be an application. So here we now have the car images again, and we have labeled it, and it seems like we have something more below. No, we don't. And when we now run some region properties of that, we look at the label, the centroid, the bounding box, then we get a table with one column for each item. And looking at this, let's see, then we can, for example, identify where we have the cars in this image. So it's actually something that is quite often is done, also in computer vision for robotics or something like that, where they really want to identify where they have people or things around for making more analysis or to avoid it or something. Then of course we can, when we have this table of region properties, we can also compute the statistics, and you could compute it yourself. No, sorry, one step ahead. So now what we can do, from within each of these boxes, we want to tell which color is the car which is in the box. And for that, we use a combination of a k-neighbors classifier and also using the web colors. So we're trying to match the color of this region, the average color of the region, with some colors, and that is what the fit is about. And then afterwards we get some names out for these colors. So it's quite a boring image because everything is kind of gray. So it's dim gray, silver, dark slate gray, etc. One is powder blue, but everything goes in more or less in the same range. And then we can see here how well this fitting matches. I think the dark slate gray is more or less, when it's too dark, then everything turns into dark slate gray. That one apparently, has some blue in it, but not so much. Another thing we can measure is the anisotropy. And first of all, what is it? Of course, so it's a kind of a ratio between if it's narrow or bulky and how tall it is. But the question is how to describe it. So here is, for example, tall and skinny, short and fat, or perfectly round. These are words, but we want to put numbers on it. And there are quite many ways how you can define it, and often it really depends on the application how you define your anisotropy. So you can see here, you can take the longest side over the shortest side, -1, or you can take the longest minus the shortest divided by the longest, and so on. So you can be very creative how you combine these. And in the end, I would say it really depends on what you really are interested in looking at. And that comes from your application. Actually, the most obvious one is not here. Actually, just longest over shortest. But that could be also added to the list. Ways to do it. Well, here's a little function that tries different of these metrics. And now we're going to show what happens when you apply these to some real measurement. So this one should animate. Seems like my slides don't behave today. I have to go back one to just make sure that I got it. Yeah, there we got it. So now you can see how this ellipsoid goes from a circle, perfect circle, until a straight line. And you can see how the different anisotropy metrics, how they behave. And well, it's a question how sensitive you want to be in your measurement, or what is the relevant thing that you want to separate between. Now let's leave that part and go into some statistical tools. And this relates to two fields in mathematics, linear algebra and statistics. And we mix them quite widely and come up with something called principal component analysis. And it's interesting when you have some data which looks at the first view, looks pretty random and decoupled. And what we can do, one is would be maybe to use k-means to find some clustering, but you find with the principal component analysis, you find distributions that are orthogonal to each other, and with that you can better separate them. And see here. So the procedure of doing the principal component analysis is first you compute the covariance or covariance correlation matrix of some images. Then from that matrix you compute the eigenvalue or singular value decomposition. So there we already have the statistical metric and the linear algebra part. And then we can use, when we have done this, we can use the eigenvectors to transform the data into these orthogonal spaces. So let's look at some spectra. This is just made up, so it's not real data, but we have three types of spectra. One is just noise, the next one is for fat, and the other one is for protein. And you can see that the fat and the protein are almost the same, but in the protein there is another peak. When we try to plot these together, it's not so easy. So we want to sort the cells into more fat-like or more protein-like. And doing this, and we try to plot these noisy things together from a certain number of spectrum, and we plot them pairwise. So we have curve 1 and curve 2. It doesn't really tell anything. We just see a bunch of spots, and nothing really makes sense. So now, if we run the principal component and fit it to the test data, now we do 5 components. And the reason why we do it, let's see, no. Okay, yeah. Anyway, so that comes on a later slide, what I wanted to say now. But anyway, if we have all these data and run the transform, and then all of a sudden we can very easily separate different components in the data. So we can really separate. We have fat-like, we have protein-like, and we have noise. And so now we wonder how important is each component in this analysis. And we now just looked at 2 components, and it seems like if you're looking at the eigenvalues of the decomposition, then you can see that most of the energy is actually placed in only 2 components. So, and that was what we showed before. You could, of course, make more components in your analysis, but it will still only give you less and less energy into that. An example where I applied it is in material science. So we want to analyze the crystal texture in metals. And this is done by doing Bragg edge imaging. So a little bit of physics coming in here now. In principle, if you have some crystalline lattice grid, then you can get reflections which are either constructive or destructive, and depending on the view angle and the wavelength of the incoming wave. And the Bragg criterion is fulfilled when you have this equation fulfilled. This can be measured using X-rays, neutrons. I do it with neutrons, and with that we can identify different types of crystalline structures in iron, for example. And the spectrum for iron is like a footprint or fingerprint of that specific crystal constellation. And then we have our spectrum, and if we run a spectrum scan over this assembly where we have two different types of iron and some other metals, then we can see in one case it appears like we have this strong edge, and in other cases you only have small reflection peaks, and the difference between them is that the one is powder-like and the other one is a single crystal. So our main interest is in the powder-like style, because then we get this pattern. And looking at our data, we look at 3 different places. So we have within the sample some kind of spacer, and we have air outside. And looking at the plots from that, we can see that we have this typical edge effect, and in the other ones we don't expect anything. Now, from the spectrum, it's very hard to tell anything where you have interesting regions. So what I did was to run the principal component analysis. A lot of steps. First we need to rearrange the data, we need to normalize it, and from there on we can run the PCA with 5 components and do the fitting on the data. And afterwards we can see here that the eigenvalues decay very strongly. We have a logarithmic scale here, and I'm still looking at the first 2, and well, the data looks quite strange, but now we have arranged it into this triangle shape which identify different regions in the data. Still, that is pretty cluttered, so one way is, first of all, when we plot it to get a better idea, we can just set the opacity of the dots to very low value, and then we can more see the hotspots where things are happening within these components. One thing that is important to say about the principal component analysis is that once you have done this transformation, you cannot really do any physical interpretation of it. It can help you to find relevant regions, but then afterwards you need to go back into the physical space again. And now I use that as a color coding, and with the color coding we can really see that these materials have actually a different distribution. So this would be the white beam image, so we take all the wavelengths, and this is principal component enhanced, and we can see that there are regions at the edges. And if I remember right, this data was laser treated to have a special surface as a surface treatment to make it harder. And well, here is another one. And then of course you can also use it for segmentation to try to identify different regions, which I haven't done here, but if someone would be interested, that could also be a little project task to play on with that. And another way of using the principal component is to compute the shape tensor. And that one can tell us how the object is oriented. And in principle, we bring up the vectors here. In principle, the covariance matrix can provide an orientation. Is in principle an orientation matrix of the data. And when we do the eigenvalue decomposition, you have a normalization that can orient the image into the most optimal way along the axis. So here we have this blob, and you see that it has maybe some kind of diagonal arrangement, and now we identify all the pixels and run the principal component analysis of it, and after that we can do a rotation which makes it more aligned to the X and Y axis. So this is another way how you can work with the principal component analysis. And yeah, you can do quite a lot of these analyses. If you have spectral data or overwhelming data, then you can use this to reduce the data amounts. It's also used, for example, in machine learning when you have too massive data input and a lot of it is almost the same, then you can reduce all the same part and take only the part that is relevant. And oh, that's another one. Okay, let's make a break here. Then we see what we can do in the next will be distance transforms that we can work with. And then we have a little break.